much do we really need as far as math and code, right? How much math do we need to be able to program effectively? Well, that's a wide question, but in the end, it's nothing crazy. So, let me kind of work through a couple of details. Let me see if I can, nah, we'll do it manually. All right. So, here's what we're looking at, and we have been looking at for quite some time now. We want to consider what parts of algebra and what is algebra, because in a sense, we kind of go through these classes, but we never distinguish the parts that are truly algebraic. Oh, well, algebra, one can consider the grammar. Multitasking here, give me a quick momento. It's the grammar of how we approach mathematics. Now, think of the case scenarios that you have the dictionary of algebra, the mathematics in general, which are just formulas that you have to memorize. Cool. Some students are really good at memorizing, so they can remember formulas. Mx plus b, for instance. Ax squared plus bx plus c for another instance. So we can remember these, but even if you remember them, the real question becomes, can you use them? And that's where our syntax, our grammar comes into play. So a lot of algebra is essentially the grammatical process in which we move numbers around. How math will align itself with uh, multiplication properties, additive properties, you've got distributive properties, you've got all kinds of little properties, little rules that basically fall within the PEMDAS syntax. Please excuse my dear Aunt Sally, right? So parentheses, exponents, multiplication, division, addition, subtraction in a specific order. Now, when we have just numbers, we normally approach this from left to right. This is the case when we only have numerical values, no variables. But when we do have an x or a y value, we do a kind of opposite operation. We try to find what is in the way, what is between the variable that we want to isolate, that we want to get by itself, and the specific number that we're trying to move. Whatever is in between them, like a plus or a minus, we do the opposite. If it's a plus, we subtract, right? If it's a minus, we add it. Now, if there's a multiplication between that variable and the number, we divide it. We always do opposites, but we also change the process. We're not going to go too crazy into the mathematics here, but I wanted to expand a little bit further into functions. And we'll see these processes again, because again, math repeats, rinse, repeat, rinse, repeat. When you see things more often, you will remember them and they'll start making more sense on a bigger scale, a bigger picture. Oh, quick momento. Get my stream and comments set up so I can see everything. Do 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 do. There we go. So let's kind of consider variables, how they work, what they do. Well, again, I always consider any variable as a box of contents. We don't know what is inside that box, but we can label it a variable. This variable will provide us at least a placement so we can kind of keep an eye on what's going on and what is in that valuation, that box, what is inside that box. But sometimes we have a couple of things happening. We've got a 3 times the x plus a 10 equals to, let's say, 40, right? So we got to figure out what value makes this happen. To simplify the drawing itself, we basically have an equation like this, but we have to find out what is inside of the box. So, like pre-mentioned, we approach it in the PEMDAS format, but reverse. We go from the right side over to the left. So, easiest case scenario. We look for addition and subtraction first, since they are technically opposites. They can kind of work in a similar order. If you find one or the other, that's your good kind of key to start there. Well, we have a plus 10. So what do? We apply the opposite case. So we subtract 10. When we do that, we have to do it on both sides. And this is what I mean by we apply the opposites, right? Not only do we go backwards from our PEMDAS valuation, we also remove a balanced both side focus. We have to do one thing on one side and on the other side asynchronously. So then we only have 3x and equals to 30 left. And finally, we still keep an eye on what's between our variable that we're seeking to uncover, to isolate, and a number in the front, which is 3. Well, this is a big key that most students forget. These two are separate. I want the colors, the visualization to be very apparent. 3 and x are not one entity. They're multiplying. They're closer than a plus 10, but they're still not one. They are two separate things happening to multiply, right? But then that brings us to the next PEMDAS case, M and D. The M and D is a same to addition and subtraction, but it's multiplication and division. So how do we basically get rid of that? Well, we divide both sides by 3 to do the opposite. Another case of using opposites to get rid of each other. Whichever one we have, do the other. And we do it on both sides as per normal. And now we can fulfill that 10 is the final x value. This is what it means to solve for a variable, is to figure out what's in the box, and in this box is 10. There's only one number that can make this sequence or this equation true. How do we check? How do we know what's the overall here? Well, we can just take the equation, take our solution that we found, and just plug it in to verify. Here's where mathematics starts to really take into a true or false case scenario. 3 times 10, 30. Oh, sorry, that was a 1. Plus 10 equals 40. 40 equals to 40. Now, from all of this, will you be programming in this format? No. But you will be using the final case relation here. When we say something is true or equal, in this case, it's a completely obvious yes. 40 is 40. We consider this truth, a truthy, if you will, a truthy statement or equation. And in programming, true or false is a huge case scenario. We do actually do a lot of falses in programming. We don't do it too much in mathematics, but it's good to really see what the equal sign means. It's a comparison of what the left side is to the right side. Now, in programming, there's a little bit of a caveat. When you do any sort of programming, a truthy check is actually normally, by most syntaxes, a double equal sign use. So you got to use actually two equal signs to activate that check. A single equal sign means slightly different, and it really does mean more like this. So in programming, storage. When we have a single equal sign, we're essentially stating this case where x equals to 10, meaning that x is 10. End of story. Anywhere we use 10, like we did over here, will be in reference to what x is. And we found out that x is 10 as we did our algebra to get there. So a single equal sign in programming is just a reference to storage. I want the left side to contain the right side. It's always a left to right. Programs, languages, they basically read from left to right, right? There's no caveat to that. Although there is kind of a processing adjustment because sometimes you can make a whole equation on the right of the equal sign, and then that language has to process that equation before it stores it. But we'll get to that point too. So in programming, slightly different from mathematics. Single equals, association. I want 10 to be x, or put 10 in a box, right? So we've got 10 or X as the label. We open up the box, we put a 10 inside, and then we close it, and then wherever we use that box, a 10 pops up. But the truthy check, the case scenario where we're trying to check some valuation to see if it is indeed true or false, that's the double equal sign. Always in most languages, I'd say in Python, it's the is keyword. In JavaScript, it is two equals. In C, C++, it is two equals. Basically, most cases, it's going to be double equals. So that's a bit of a caveat to remember because in the end, they're just slightly different, but they still reference something within mathematics, right? X equals to something, store that information in X. X is going to be plugged in wherever we see that value, that variable. But then the other use for an equal sign is that truthy check to see if it is indeed true or false. So this is kind of the basic structure. Hold up. I was doing some other stuff down here, talking about the construction of certain things. So the equal sign does have a two-sided purpose. Comparing two sides if they're numeric and making sure that they are indeed equal, which then we know that we got the problem correct. That's in the end case scenario. If we find that 40 equals to 40, that actually supports the fact that our number 10 is indeed the answer for x. So in math, you can always check yourself and make sure your problem is correct. Case in point, right? So that's just the kind of more advanced usage of variables. Now we want to go into functions. Functions in the form of math, there is still a relation, right? There's a logical type of relation. This is where we use these sort of annotations. F of x. This is where you can say, yes, this is one thing. I know, it's a little weird when we see a 3x and we say, oh, wait, how can 3 and x be different? And they're multiplying, but f and x are not multiplying. I wish I started this in a different format when I first began in mathematics, but you're right, this is a confusing factor. Why is 3 times x here on the top, but the bottom is a function? Well, I guess the case scenario here would be parentheses, keep track of the parentheses and also keep track of the location of f of x. Normally we don't use f, p, q, any of those particular values. This is kind of why we try to keep x, y, and z their own little consistent use when you're doing algebra problems. And then f, p, q, those would normally be a type of function name, right? So f is just a name for a function. We have also q as a function name and p, and these are the most common when you're dealing with any mathematics in the course, with algebra, etc., etc. But if you don't have one of those variables, that's one of the hints you can kind of separate them by. You don't have a p, you don't have a f, you don't have a q. You're probably dealing with a regular multiplication, like 3 times x. In this case, function, how do we say those, right? Function of x. So that's a key to distinguish between the two. But functions basically can be identified because normally they're on one side alone, and the equal is associating something related to that function, a type of algorithm, an equation, something that we can store and reuse and save, almost like a variable. Now, in programming, slightly different. It's a block of code where it's multiple lines of code. But when we're dealing with functions here, normally it's going to be like 2x plus b, 2x plus 10 or something, some linear equation in our case. Or it can be a quadratic as in 2x squared plus 3x minus 20, something like that, right? So what this basically states is I have a complex combination, an expression that I want to save into this function named g. That's the association. And the same for the bottom, I have this less complex, but still decently complex, and I want to save it in there. And then we go into nesting functions, one function inside of another. A little bit of an extra feat there, but we'll get to that point. But this is kind of how functions work as a container. Now, when we do programming functions, luckily, we have flexibility. We can name them anything we want. We just have to declare it to exist. So we have to have a specific keyword. In JavaScript, it's going to be the actual word function. We say that first. We type it at the beginning of the line, and then we'll say function, my custom function, whatever you want to name it. This is just an example. You can name it anything. Add, subtract, divide. Basically, anything that's not already taken from the developers that created C++, because you've got certain functions that exist already, some key sets of words that actually exist. So as long as we make ours a little bit more obfuscated and quasi difficult, in this case, my custom function, probably not going to be an existing name in the original system of the language itself. But the one things you'll find is that we technically do have something of a similar format. Our key and mathematic function becomes a much nicer, flexible naming convention. We still have something that we consider to, why do you keep doing that? We still have our parenthesis. Stop changing on me. The parenthesis that stakes over here. And we do use this parenthesis both in mathematics, the same as we do in programming. That's the one real kind of exact same thing that's happening here, the exact comparison. Now, you can have a function though without any of anything inside parenthesis. But what is the parenthesis? It's basically an input. We want to input some variables, one, two, three, four of them, doesn't matter, however many we like. And then we actually apply them inside of the function. Well, that's not so different because if we take a look at a case scenario here where maybe I put p of 2, well, I'm kind of applying a similar notation here. When we take p of 2, we're actually saying, hey, x, I want x to be 2. Well, what is x? X is this guy right here. So we take our x, we copy everything the same. 2 stays, the regular 2. In fact, I might want to readjust that for another value. Let's do 4 so we can clearly see the differences here. So our x is going to be 4. And then instead of x, we would essentially put a parenthesis around it and then plug in the number 4 for that particular case. That's exactly what x is in algebra. It's a input into the function. So it basically helps us change values dynamically. We can do 4, we can do 5, we can do 6, we can do 7, any number that we want to test out what the line will look like or what the graph will look like, because this does indeed make a line. Now, that same idea happens with custom functions in programming. Whatever we plug inside of that parentheses set, we end up being able to use it within the program. But where is the program? Well, we haven't talked about the code block itself. It's always between these curly braces. Very similar to how our technical equation is just on the other side of the equal sign. But remember, in programming, you can have 1, 2, 3, 5, 10, 20 million, 100 lines of code. And we can't really make 1 million lines on a single line, otherwise you'd be reading from left to right forever and you'd be scrolling to the right, constantly trying to figure out what the code is doing. There's a sense to why we program with enters and returns and try to organize ourselves. So what would normally happen with these curly braces? Well, they'll actually look a little bit different. It won't be like this because there's no way we can fit code in there. Obviously, it's very tiny. So we'll take that second curly brace, move it down somewhere over here. Now we probably have a couple of lines of code. We can say x is equal to 2. We can say y is equal to x plus 5. And then we can say print y. And now this will be a case where we basically put in a function, and the function itself contains the code. Now, what would I be if I wanted to actually make this equation into a function? That's actually a decent kind of comparison here. First, we'll state that our p is equal to 2x plus 10. In fact, we may need to do this in order. X doesn't exist yet, but what we can do is input x, just like we have over here. So we would input x through that parenthesis input space, and then we say this variable p is equal to 2x plus 10, which essentially mimics the equation that we have in the algebraic format. So we're actually doing kind of a one-to-one comparison between how do I convert an equation and code. So luckily, programming can basically do addition, subtraction, multiplication without extra oomph. Maybe for like exponents, we may need to use a function called pow, or in other cases, some languages like Python will have like 2 asterisk asterisk 4 would make a 2 to the power of 4, but we can also basically customize that as a function itself. Now, when we plug in our input x, and we say that, well, and then let's say we want to print it, because right now it's not going to do anything. We're going to print p. So if we print p and we run our function, we just got to remember one of the key caveats here. A function does not get activated until we use its name. So here we're kind of like at the beginning of the file, call this line 1. And maybe down here, 1, 2, 3, 4 on line 5, we're actually going to call the function and input our 4. This is where we actually run the code, and line 1 with function defined is where we create the block. Creating that block gives us the ability to save that code for whatever we need to basically use it. We can use it anywhere we'd like now, and we can even put this in a loop that repeats and goes through every single value from 1 to a million. Takes for a while to get it through. But that's essentially how we have functions relate between algebra to programming. Now we have the other case where we can basically plug a function into a function, but I'd say that's a bit more advanced and up to further understanding in the future. For now, we're essentially just kind of reviewing what the basics are between variables. If you're not familiar with variables, now should be a good kind of comfort space to understand that variables are just basically boxes with labels. We put numbers inside, we manipulate, add, subtract, whatever, and we use those variables in any case that we see that same exact mention. So for x, we will plug it into this location, do the math, and continue forth. So that's it for now. This is the essential structure that we have when we're thinking of how does math really relate to programming. And it really kind of stops at this. When it comes to the mathematical sense, of course, we know that programs code can do addition, subtraction, all those valuations, but now we have a direct relation. So if you're good at programming but not so good at math, this should synchronize that concept and now be like, oh, variables in math, yeah, they're basically the same as a variable in programming. Except in programming, we can change them to whatever we like, any naming convention possible. Other case scenario, we can now see if you know math, but you're not too sure about programming, now you see the other case too, where a math equation can be represented into a actual programmatic function. In this case, something similar to JavaScript. So that relation now should be pretty clear between what a function looks like in one case in mathematics and then what it looks like in a programming space. And not only that, but a little bit more in depth on the types of use of a variable, what a variable does, the truthy check in programming, making two equals be that truth check to see if this case is true or false. And then that's when we can basically do if statements, for loops, while loops, And those are all controlled by a truthy check, a case for trying to figure out if something is the same on both sides of our equation. On the other case, a single equal sign, just a single equal sign in programming is just storage. We're taking whatever is on the right of that equal sign and associating it to the left. That's what variables essentially do. So that's it for this video. Hope it helped out some people. Hope that you enjoyed the content. And I'll continue on making small little videos here and there and streams and yada yada. But if you do care to have any questions, leave them in the comments below. If you want me to go over any specific language, any specific idea, maybe you have questions, perfect. Leave it in the chat. If I'm not live, leave it in the comments. And like and subscribe, and we'll continue.